All right. Okay, so here we go. We're going to be talking about scanning, physics, and instrumentation. But before we get in that, we're going to look real specifically at physics, okay? Yeah, lots of fun. So everyone stay awake. It's one of those things that's like, we all grow when we have to study physics or whatever, but we're talking about stuff that is like particles and collisions and tremendous amounts of energy being released, and the more I talk about how much energy is being released, it's like the more y'all's energy just fails, right? But in terms of an overview, we're going to be talking about radiation physics, so interactions with matter, and then acquisition geometry. So when we're talking about CT, we're talking about spinning this stuff around, right? And that's what I mean by acquisition geometry, okay? And then that shouldn't, right there, let me see if this little fella even works. This should not say helical scanning right here. That should say, I don't remember what it's supposed to be saying, but disregard that. So, in terms of radiation physics, and these slides are available on Moodle, I think, we can talk about target interactions, right? And so when we're talking about target interactions, we're talking about interactions inside here, right? Inside this thing, you know? And then we can also talk about, and the primary target interactions are Bremsstrahlung interactions and characteristic interactions, okay? Then we can talk about differential absorption, and that's generally the way we talk about the interactions inside here, inside the patient, right? And so that's going to be photoelectric effect, Compton effect, and then kind of attenuation and transmission. That's kind of what we're talking about over here, is how it's transmitted to our image receptor, right? So that's kind of a general overview of what we're looking at. Radiation physics, target interactions, Bremsstrahlung interactions. Bremsstrahlung is just the crazy German word that we use because it was some German guys who discovered it, and it just is a long word for that means breaking or stop, right? It's like, has anyone ever seen that YouTube video about German compared to other languages? We can watch it in the break. Because this will really help Bremsstrahlung, settle in. It sounds like the name of like a really bad like heavy metal band, right? Yeah. But it just means breaking or stopping. So the electron travels close to that end should be nucleus. Look at this, you can write on it. And then it changes direction, right? And an X-ray photon is produced, right? So here is an illustration of it. So we have this incident electron, travels real close to the nucleus. The gravity of the nucleus pulls it in a different direction, and then a photon is emitted, right? So particle, electron, moves close to the nucleus, and a photon is emitted, right? Kind of the significant thing for us here is that this is like 85 to 100% of what's happening inside of the tube, right? Predominance is Bremsstrahlung radiation. The thing is not only is a photon emitted, there is heat emitted as well. So it's a very inefficient process, but this is largely how we produce X-rays. In terms of other target interactions, other things that can happen inside this guy here, the other thing that we talk about is the characteristic interaction. And I just think about this being like the trash interaction. Boring old characteristic interactions where a projectile electron ejects a K-shell electron, and then an outer shell electron drops into the K-shell, and a photon is emitted. Now that photon's going to be pretty weak, and it's not usable for diagnostic X-ray because it's something that would just hit the patient's skin, be attenuated, give us no information. So that's why we have, that's largely why we use things like filtration. We want to filter out characteristic X-ray production from the patient because it just contributes to the patient dose. It has no diagnostic value. In CT, we're going to additionally filter in kind of a shape. So this is what this little bow tie is up here. In CT, we use a bow tie filter. Let me try drawing it on this thing rather than on the whiteboard. So because my body is basically tube-shaped, we're all like hot dogs walking around, right, according to the physicists. So I'm basically hot dog shaped if you look at me like axially. And so I can apply a bow tie shaped filter to that, and it's going to filter out the x-rays on these sides, right, more, because we're imaging something that's basically tubular. Does that make sense? Okay. So let's look real closely at, I guess. So incoming electron, again, it's a particle. It ejects another particle, and as that particle exits, another particle from one of these other valence shells is going to drop into that spot, and depending on what valence shell drops in, it's going to emit different energy x-rays, right? It's largely dependent on where it was in the valence shell, what the energy of those x-rays is going to be. Do y'all remember my goofy mnemonic for how to remember valence shells from last, when I just kind of beat you over the head with radiation physics last semester?
That wasn't us. We had already physics.
It was some people, it was y'all, the radiation therapists. Does anyone remember? Okay, I'll tell y'all anyways. So, kinda low mass negativities. That's how I remember electrons, right? And this gives me a way to remember, what am I drawing right now?
Shells.
Valence shells, right? So this is how I remember how to calculate the number of electrons in the shell, because I know that, 2n squared, right? If I plug in like k equals 1 in this formula, so in the k shell there's a maximum number of 2 electrons that can be in that shell, right? Versus n is, the n shell is going to be the 4th shell, right? And so n squared is 16 times 2, 32. So there can be upwards of 32 electrons in that n shell, right? There can be more shells than that, but this is the predominance of elements that we're dealing with. So just a goofy little mnemonic.
So what was the N for again?
Kind of low mass negativities, but then in this formula, the N means the valence shell number. Okay? So in this formula, K is 1, L is 2, M is 3, N is 4. Does that make sense? Okay. There will probably be a board question about that. Oh, no? That's right. Okay. Okay, so kind of low mass negativities. Kind of low mass negativities. So in radiation physics, we talk about differential absorption. This is kind of the umbrella term that we use for talking about the interactions that happen inside of the patient, right? And in CT, we're trying to measure those different kinds of ways that x-rays are absorbed by the patient, and that's what we're trying to record with the receptor, okay? So, so variations in absorption and transmission of the x-ray beam structurally represent the area of interest, right? Now, I know there's a whole lot of kind of nerdy language going on there. We're going to pretty much spend the rest of this class kind of unpacking what that means, but just keep that in the back of your mind, that we're talking about variations of absorption of the x-rays and what are absorbed, what are transmitted, and how that can structurally represent the area of interest, which is the patient's body, right? Okay. Now I have no clue what this lecture software is doing. All right. So in terms of differential absorption, things that are happening inside the patient, one of the ones that we're really interested in is the photoelectric effect, right? So this is a case in which an incoming photon, now we're no longer talking about electrons, we're talking about photons, we're talking about like this wave-particle duality kind of thing, right? An incoming photon removes an inner shell electron, so a K-shell electron, and then an outer shell electron drops into the vacancy, emitting a secondary photon. So the total this results in the total absorption of that X-ray photon, right? But the emission of a secondary photon. This sounds similar to a characteristic interaction, right? The key difference is that a characteristic interaction is talking about a particle. It's talking about an electron hitting another electron. Now we're talking about a photon hitting an electron, right? So the graphic representation of that, we have this photon coming in here. work, dang it, there it is, right there. Knocks out this K-shell electron, it goes out, and then when this electron drops in there, it emits a secondary photon in a different direction, right? It's going to be a really low energy, useless X-ray that's going to really be very quickly fully attenuated, right? This electron here that's been knocked out of orbit, though, this is what we're talking about when we're talking about like free radicals. These things, this atom can now go on to bond with other atoms, you know, and what form like hydroxase or something like that, which then can damage the body. It's like an alcohol. Okay. But the main focus here for our purposes is this photoelectric effect radiation. So that's good stuff, right? When we're looking at our image receptor, we want to see photoelectric effect because it's going to show up white on our images, right? This is areas of the film that were attenuated, and so the image receptor didn't receive any information. Therefore, it says something there has a high enough attenuation value that that we're going to call that. We're going to tag that with the color white, right? So like a bone, right? Compton Effect is not good. This is the bad guys. And I always think about that song Straight Outta Compton, right? Like, people should get along with each other, you know? You're just like hanging your head. Sorry. That's how I remember it. Compton Effect, aka Compton Scatter. An incoming photon ejects an outer shell electron. It changes the photon's energy and direction, and it depends on the energy of that incoming photon. Looking at that, here it is. Incoming photon knocks out this this like L or M shell electron, and it just pings off at a different direction, right? The significant thing about this is, let's pretend that over here is our tube that's emitting X-rays, right? And over here is our receptor that's receiving X-rays, right? And this is like a bone in the patient's body that has this atom in it, right? If this, we want either the X-ray to strike this thing and stop, and then show up as like a 1 on our receptor. It has an attenuation value. Or we want it to pass straight through it and, you know, darken the receptor, right? What we don't want it to do is spatially now to go off in this other direction and hit the image receptor down here. Because that's not like where that atom is at, right? So it has now spatially placed this atom down here. So we have a loss in spatial resolution. Does that make sense? So we have to figure out ways to get rid of the Compton effect. In X-ray, we use grids and things like that for that purpose, right? Algorithms that we apply to it. So, thinking about differential absorption and how this really works in terms of computing this information, right? We need to think about the factors inside the patient that contribute to different kinds of beam attenuation. So that's going to be like tissue thickness, right? The type of tissue. And then X-ray beam quality, right? In our book, I think it's like figure, it's on page 6. If we open up our book to page 6, we're going to have a nice, neat little representation of how these different, table 1.1 gives us the linear attenuation coefficients of different kinds of tissue, right? And the reason this is really, really important to us is different things have a different linear attenuation coefficient. Coefficient is just a fancy word for like multiple or factor, right? It means that you can apply a variable to it and it's going to affect that variable somehow. So, but if I were to draw a really nerdy picture, right? This is going to be a terrible picture of a bone, okay? And then let's say we have a muscle attached to that bone. So here's a terrible muscle. And then this person also has some fat, right? So this blob up here is like fat. What this is telling us is that these things are going to have different kinds of attenuation, right? So, like bone is going to have more. It might be like a 2, this would be like a 1, and this would be like a 0. Just hypothetically speaking. This is going to be high, this is going to be like middle, this is going to be low, right? I'm writing like a 5-year-old on this. So, is there a way to erase this chunk? Yeah, I guess there is. Okay, whatever. So the reason I want us to kind of think about that for just a sec is thinking about linear attenuation coefficients and stuff. I'm not going to ask y'all to work this formula out, right? Yes, but the ARRT may not be so kind, right? They may ask you to be able to work this formula. So we need to know kind of how to express this formula and how to kind of think through this formula. So does anyone remember from my last physics lecture how I suggested memorizing this stupid formula, or the natural log of 2? It was Saturday Night Live, right? So natural log of 2 is 0.693. 6 starts with an S, 9 starts with an N, and then there's 3 letters in Saturday Night Live, right? SNL. So the way I remember linear attenuation coefficient is, I know I'm drawing on the very bottom of this thing, but if I want to have a laugh, I watch Saturday Night Live. Have a laugh, HVL, right? Half value layer, have a laugh. That's going to give me my linear attenuation coefficient. Okay? Just another goofy mnemonic that hopefully helps folks remember this material. All right. Different way to think about it. The way that we measure linear attenuation is even more exciting than this lecture. What we do is we apply amounts of aluminum to the primary beam, and then we measure how many photons are there after they pass through the aluminum. And so we've linked now the linear attenuation coefficient of different tissue to the linear attenuation coefficients of different amounts of aluminum, right? And that's largely how we measure beam attenuation. So in this case, we have a linear attenuation coefficient of 0.1 per cm, right? So that means if we had 100 photons passing through that material, 90 would come out the other side. Basically 10% has been lost. Does that make sense? Okay, moving along. Here's another way of thinking about it. This is kind of progressing along in our book to table 4.1. This is tying linear attenuation coefficients to what? To Hounsfield units, right? And the importance for that, and kind of what we're going to be talking about in this next lecture, is this is tying the physics of what we know about linear attenuation to instrumentation of how we do this stuff on the computer. All right? So I'm going to show you what I like to call the boring CT party trick, where we actually are going to represent, I'll walk you through what the computer's doing when it's using this information of linear attenuation coefficients from the receptor to then compute an image, right? But just be aware that these different linear attenuation coefficients, the main way that we're thinking about them is we're tying them to Hounsfield units because we can visualize that. Like that's going to pop up on our image display, and then I can drop an ROI on that, a region of interest in that area, and it will tell me how many Hounsfield units are measured in that area, right? So it's a computer tool for us. So that's pretty much all of the what I would call radiation physics, right? That's all of the things that have to do with interactions inside the tube, and then interactions inside the patient and the way those are recorded by the image receptor, right? But kind of the last step in this is if we're talking about CT, we're talking about spinning things around, right? And so we need to talk about the kind of geometry or the physics of how we're acquiring these images, right? And the two big critical things here are pitch and effective mass. Okay? So pitch is the amount that we're moving the patient as we're spinning the table, right? So the amount that this moves as it spins, right?
Can you say that again?
Pitch is the amount that we're moving the table as we spin the tube. Okay? So if we're looking at the z-axis, right? So pretend this is the z-axis. Pitch is talking about the amount that we move this for each time that we spin the tube around this, right?
Oh, okay.
Does that make sense?
Yeah.
Okay. Effective mass has to do with the S in mass. What does S mean in mass? Seconds. So it has to do with the time involved, okay? So the dosage that we're giving over time as we make these movements, okay? But that has bearing on geometry, as we'll talk about here, because in which we need to spin this thing around. So effective mass is basically the calculated mass per acquired slice. So for every spin that this receptor makes, the amount of mass that it took for it to complete that spin, right? So the main controlling factor in this is going to be table speed, right? So the faster we can move that table, the more we can decrease the patient's dose, is what this is telling us, okay? Pitch controls the table speed. So all this stuff is kind of interrelated, right?
Can you say that all again, like the detector pitch until effective mass? You said what was the detector?
I know I'm talking kind of fast. And no, that's a good question. Just to repeat, and we're going to be unpacking this more. We're going to get down to like the numbers, like how to calculate pitch, how to really figure all this out. But effective mass is the calculated mass per acquired slice, right? So, yeah. So basically what it's saying is the amount of time it took me to spin the tube around, applied in milliamperes, right? Milliampere seconds, linked with this movement of the table along the z-axis, right? So that's what this formula is giving me right here, right? It's tying the dosage to time and table movement, okay? And I promise you, we're gonna make that super exciting by the end of this day. So, like kind of a general overview of CT system principles. We're talking about data acquisition, right? So we're requiring largely linear attenuation coefficients. We're measuring linear attenuation coefficients of the body as we're spinning this machine around. Then we're using a computer to reconstruct that information, to spatially represent that information in a way that makes sense to us, and then we're displaying that information. That's all we're talking about. But that's largely how instrumentation works in CT. So we're taking this physics of how radiation is created, attenuated, or transmitted, and then we're applying that to instruments that can measure that. Okay? And those instruments are largely have to do with data acquisition, computers that can reconstruct that information, and then monitors that can display that information. Okay? So, quick about that. One does not simply read a CT scan, right? Yes, I'm just letting my nerd flag fly today. All right, well, y'all take 5-minute break, and we'll be back.